maybe.
Okay.
Alrighty.
So I've got the agenda of 4 things today. First of all, I just want to do a live analysis to see what's going on with Floyd 3, kind of a health of the system check from the beginning. We'll take a break, then I want to come back and take a look at a real system info gather report example. Another break. Then we got to cover OpenMP, take a break, cover MPI, and then I'm hoping we have time to do some NUMA, to start the NUMA lab. I'd like to get boot CPU set and the user CPU set in place today and be ready to use things like dplace tomorrow morning for our demo. So that's kind of the agenda. Okay, so I'm just going to start off here and log into Floyd 3. And by the way, there are times where you can't log in, but you can still ping it. That usually means the OS is up and running, but the OS doesn't have enough memory, or page cache is under such pressure that it can't get the login process or the login executable in from the file system. If you can't ping it, then obviously there's something much, much more severe, and then you go to the serial console and see what's going on there. Okay, so just starting off topology, I want to see what I've got here. I got to have perspective. So again, this system is 4 UV1 blades. They're not going to change the terminology of a node, but a node is not a socket, not really a hub, but it is a node in the interconnect is really what it is. It's something in the interconnect. So 64 CPUs, 252 gig of memory. Again, it's really closer than that, 256, something like that. Do not expect the memory numbers to all match. Some are powers of 2, some are powers of 10. Some may take PROM out and stuff like that. And then LSCSI, so CPU memory, 2 base I/O disks, and then we've got 2 paths to a 5-LUN RAID. Okay, and if I do a CPU map, this is important for CPU sets and stuff too. I see that I do have hyper-threading turned on the system. This is a Nehalem. So I've got 8 sockets, 8 processor packages that are plugged into these motherboards. With hyper-threads, that's giving me 32 cores or 64 CPUs. And if I'm going to make a boot CPU set today and a login CPU set, I may just take the first blade, which is kind of too much really, but I don't, because they're both sharing the same, well anyway, I might take the socket actually too, but I might want to decouple the entire blade so that any traffic going on that blade does not step on my batch work. So in reality, I might take these CPUs for a boot CPU set and these CPUs for a user interactive login CPU set. I will, in this class, probably put the boot CPU set on these CPUs and the user login CPU set on these CPUs, but the problem is then they're both sharing the same memory. And then somebody logged in interactive could write a file and basically lock out everything on the system because it's all dirty memory. And when we were talking about flushing stuff, the flush daemon does not work on a per CPU set basis. So if my CPU set is less than 10% of the physical memory on the system, I could fill up my entire CPU set with dirty data and then be unusable. The thresholds are not on a per CPU set basis. So I'm just doing a quick inventory here. And I do have that RAID that we looked at earlier, and it was really part of the second week. So I've got an LSI device here with XVM. It's stripe 2 wide concatenated. The 4 LUNs are basically a 2 wide stripe concatenated twice. I also have a partition here that is basically the leftover space on that root disk. I don't know why engineering splits that off as a separate file system. I'd rather call that thing /temp or do something else with it. A customer has to be able to know how to get that disk space back have a second disk drive in here. I should warn you, I do not have LSI PROM hardware RAID mirroring configured here. I need the second drive for training purposes. If I do an LSCSI, oops, everything has a name except for these virtual things. I can't do it from there, sorry. Let me go to a different system here for a second. Okay, try a different one here. LSCSI, this is what a hardware RAID would look like. This is happening at the PROM level. When you're booting a XE brick, you can use like Control C and drop into the LSI util during the boot process. But on a UV, you need to bring the system up on a DOS fat type of file system and have LSI util there to be able to configure a hardware RAID mirroring situation. So if I did an LSI util here, I could then see that those two drives and their serial numbers make up this logical volume. Any questions on that?
Nope.
I was just trying to show you what a hardware mirror RAID root would look like. Okay. DF-H again. My root is about 52% full. One thing that's really painful is when you do start filling up file systems to know where the disk space is being consumed using things like DU and stuff like that. But it's never really fun finding a disk leak. So I have to watch for that. It's always a good idea right after installation to run that system info gather to see, you know, how big things are in each of your sub-file systems. And system info gather does have a DU section on it, but not on a single V. You have to have multiple Vs because DU can take time to figure out disk space usage. Also have an NFS home directory. So that is a quick CPU memory disk file system. I better check something else here as well, DFHI. Notice I do have a file system here that is in a out of inode situation. 137 million inodes on that file system.
Mm-hmm.
Okay. So I'm just going to start off with a SAR 1-5. A little bit of I/O wait time there, a little bit of system time there. Again, I'm looking for a healthy, unhealthy situation. So the I/O wait time is probably of most interest to me at this point, but I don't know what it is. I want to quickly go through all the resources before I come back to workload characteristics. But I am interested in that system time, but it is under 10%, so I'm not too interested. The I/O wait time is probably more important to me right now. SAR-R 1-5. So I do have a memory, out-of-memory situation here. I've got 99% of my memory used. Let me try to get this. Oops. And again, SAR doesn't really give me the detail that I want. But breaking it out, what do I got here? I got a 264 gig of memory being used. That's 99% of my memory. and 222 of that is the cached field. Okay?
Mm-hmm.
Also, commit is what the applications have reserved. So I've only reserved 11% of my memory here. Not an allocation, but a reservation. Again, we can over-reserve, and the percent commit can go above 100. There is a sysctl parameter, overcommit. If that's set to a 1, then I cannot overcommit my memory. By the way, let me grep commit. This commit limit is my virtual memory size. It's basically physical memory plus physical swap. But I have a ratio here. And this ratio is going to affect the commit limit. And again, we can overcommit, and this isn't relevant unless the overcommit memory is a 1. But let me do a more on proc mem info. The default then is to take swap plus half of physical memory. So this is saying my virtual memory will be half my physical memory plus my swap. So I take my physical memory, 264, cut that in half, 132, plus we're going to add swap to it, making it a 142. So the way that limit is working is we take the ratio times total memory, and that was 50%, and then we add swap to it. So that should give me a commit limit. There we are, 142 gig. Let me do a sysctl-w vm.commit. What was it, ratio? Oops. Commit underscore ratio, let me make it 100% now. And we were at 142 gig. Oops, what did I do wrong? Overcommit ratio. Here we are. Now if I take my commit there, now we're at 274. So that's saying 100% of my memory plus all my swap. So it's 264 plus 10, that's 274. So I've just changed my virtual memory size, what I can reserve. But again, since overcommit is a 0, we are allowed to overcommit, and this number is pretty meaningless. I get into that more in the advanced sysadmin class. Let me go back to any questions?
Nope.
So I always like to go back to see if I'm still in the same situation I was before. It's pretty close. System time is a little bit higher than it was before. IO8. So we're in the 3%, 5%, 6% range there. *R, 1-5 is what we were looking at. So all my memory is being used. Most of it is cached. And again, I'm trying to reinforce what can be in that cached field. We don't know yet. No raw I/O. Okay, 8 meg is nothing to worry about there. And I was just explaining this, which is really pretty meaningless. If I had been the engineer on this, I would not have put that on this particular column. I would have preferred to keep my swap information there so I can see physical memory and physical swap on the same report. Any questions right now? *big S 1-5. Not too bad. Obviously, I have 22% of my memory, or 22% of my swap being used. I don't know of any easy way to find out what's on the swap device. And so I've got 2 gig of the 10 gig that is swap. We don't know what that is yet. Let me come back to that now. I'm going to do a *big W 1-5. This is telling me swap I/O, and I do see that I do have some swap I/O going on. I'm going to do a *big W And I can see that I've been doing nothing but page outs. There's no page ins going on. It's all page outs. So whatever's swapping out to the swap device is not being used and coming back in. And again, when I'm in a memory pressure situation, we do not swap executables. They're just released from memory, and we go back to the file system to get them. We don't swap the executable. So something is trickle swapping out. It's not heavy, but there's definitely swap out activity. Again, we're out of memory. Any questions?
Nope.
I'm going to do a SAR-big S. And I can see that it has been growing slowly. Let me go into var log SA. I'm going to look at yesterday's date. Today's the 13th, so SAR-big S-F on SA12. And I can see that this event kind of started about 11 o'clock yesterday morning. And then the real event started about 6 o'clock in the evening. And it's been slowly growing since. We okay?
Yep.
So CPU, memory, disk, let's do a SAR-DP. Since we got swap, I would expect to see something there. D for disk, P for pretty. Again, it's kind of hard. Ooh, we got a bad wrapped number here. I've been complaining about that. You got to be able to know when to throw data away. So I don't know what's going on here yet. SDI has got a problem on it. Let's see what else is going on here. I generally, when I do this to start off with, I like to just grep for average so that I don't have too much information here. And again, I'm going to live with this line wrap here rather than drop the font down right now. So my root disk, DF, my root disk is SDA. And just looking at SDA to see how healthy it is. I don't have a, let me do this with a header first. SAR. Good enough. So looking at my columns just for SDA, these are the number of I/O operations. An IOP is a single packet request that's going to get to the spindle and tell it, position your head at this block and then transfer a given number of blocks. That's an I/O operation. Again, we'd rather do large sequential IOPS than do lots of littles. We don't want to spend all of our time in handshake protocol passing IOPS around. And I got my bandwidth. By the way, I can see SDB has also got something going on during the past day since midnight. SDA, however, does have a lot of writes going on. And again, this is an average for the day. Average request size in blocks or sectors. So I have to multiply that times 512 bytes to get a request size. It looks like little, small, but notice SDE has much larger request sizes. I do wish those were in K bytes or something like that rather than blocks. Average queue size, number of I/O operations queued up. And then we have our wait and our service time. Now, my rule of thumb, I want these two to be less than 60. And again, this is an average I/O wait for all the IOPS. If I want to look at each individual IOP, there's block trace to do that. And then lastly, busy. So my route is borderline. I don't have any real concerns about it. And again, I know that there's swapping going on to it right now. But my average wait time is borderline, not too bad. And again, my busy is not very busy. Now, I don't want to get into interpretation of that data right now. But looking further down here now, SDE and SDI, I see some on SDG. Interesting that SDD, SDF, and SDH have no I.O. going on to them. And that's because of the way the file system is built and allocation groups and the fact that it was a two-way stripe concatenated 2 times. So we're still on one of the first concat objects. ls-l /dev. Well, let's do it this way. ls-scuzzy. D and I are the same device. And what did I have here? So I had E and I, G and K, it looks like. So E and I are 2 slices to the same partition. And then J and K are another slice. Again, I would have to go into XVM show-T-E to map them back. That's not really the subject of this class. Now, to take that one step further for live, now that I've got a baseline, if I do a top disk, I'm looking at it live. I'm seeing SDB busy, SDK, SDG. And again, the hard part is being able to map these back to the actual file system and then the process that's doing the I.O. So I know that these are mounted as /SCR, that's an LVM file system. And SDB is not, and XVM is just the second drive there with a lot of reads going on it. Any questions right now?
No.
So the biggest extreme case I see was the I.O. that was going on up here. This is the biggest concern to me, to find out what's going on with this I.O. Secondly, then, we do have IOH showing up, and thirdly, we have a little bit of system time. So in terms of shaking out the system, the disk activity in I.O. is the biggest concern to me. Okay? I'm going to go one step further here now. I want to go into top now. Oh, before I'm done. So CPU memory disk. The next one was file system buffer cache. Let me go into proc. If I can spell it right. So I'm pretty much out of memory. 511 memory free on Meg. sysctl-a grep for free min_free. And you can double this because there's 2 zones. I've got a PV on this. But basically, 500 meg is what the kernel is going to try to keep free on the system. And that's pretty much what I have here. So we are hitting min-free kbytes, it looks like. And that's why we have some trickle swap out going on. But we don't know what's causing any of that yet. And then also looking at this, again, I see most of my memory is being used, and most of it is cached. Most of it is inactive. In fact, most of it is inactive file data. And after that, it looks like we've got a lot of active file data still that's actively being used. Not a whole lot of process space, not a whole lot of data or stack segment here. Okay, we'll come back to those later. I don't know if I'll have time this week to do a swappiness experiment to control that, but so here's my swap free. So I got about 2 gig that's allocated on swap. Ouch! I do have dirty data, and we know that we're flushing. Boy, I got 76 gig of dirty data. 33 meg of write-back data. Only 4 gig of process space. So here I got a 264 gig memory, and my applications are only taking 4 gig, yet I'm out of memory. So everything is in this cached field. And of that 211, the dirty was 76. Okay? And I see another thing in here now. 23 gig is shemem. Okay? Of that cache field, 76 was dirty, 23 was shemem, so that's about 100 gig, but I still have 111 gig that's in cache that I don't know what it is. And I also want to check the slab here. And my slab is at 46 gig. I don't like a kernel or a slab that big. Any questions right now?
Nope.
So I want to find out about that shemem to find out if that is productive. Again, at this point, I'm an efficiency expert. I want to know what's in the slab. It appears that I have some cache clean, maybe 100 gig of cache clean here. Now watch here. I got 211 gig of cached and 46 gig of the slab for the kernel, right? Bring up top. 215 gig here. Hang on a second. What it's adding into there is what's reclaimable. So this is interesting to me. Out of that 47 gig slab, 37 gig cannot be reclaimed. So when I was talking about it adds the slab, it's really adding the slab reclaimable to that cache field. The thinking being, and this is wrong thinking, that if I need memory, I should be able to get all of that back, when in fact I can't. Some is going to be dirty, write back, NFS unstable. Okay? Some of it is unreclaimable slab. So that, and let me do a free command. So I've got 215 gig up there and 221 gig here. I don't like the way they do all this, but so there's my 211, and then here's the other 10 gig. Okay? So I do have a large slab. I do have a lot of dirty data. So my file system buffer cache, all three are under pressure. File system with a 40 gig slab. Of course, I don't know its file system really because 37 gig of that is unreclaimable, and I don't know what that is yet. How am I going to find out what that is? What command, Gus? Slab top.
Yep.
Let me do a slab top dash S space C and see what that 47 gig slab is. I always sort by C. Dash S space C should be the default. Oh, what we got here are file pointers. Open file table file pointers here. What do I got? 37 gig of that is this file pointer stuff, open file table stuff. And then I have a almost a gig of buffer head, but right there, that's most of what my space is. So that's file, open file stuff. Notice my iNotes and directories are pretty small, far down on the list. Any questions right now?
No.
So it appears that's not reclaimable. I'm still not sure why we're swapping when the cache field appears to be mostly cache clean and reclaimable, but let's take a look at that here in a few minutes. So I did a quick look at CPU, and I saw IO wait. I saw a little bit of system time. So I do a perf top. Again, be real careful with this in older releases. It can deadlock your system. It is still not safe if you have multiple perf tops running. But even in SLUS 11, a single perf top can deadlock your system, and NMI won't even work. It's taking a little bit to do something here. It would be nice to have a crash or something like that. Let me see here. Remember what we were saying yesterday, folks? The hard part is being able to catch it before the problem goes away. And by the way, I have CSA accounting running. This is not good. I can't even log in right now. If it had panicked, I wouldn't even get that far. Oh, what happened here? Got a timeout on it. Uh-oh. Not good. What should I do?
Oh, you can't ping. Interesting.
I got to go to the serial console. Unfortunately, I think we just lost everything. Let's just start off with a power status. Everything looks okay there. I'm going to do UV con. I need to see the serial console in case it dropped to KDB. And it did. I'm just looking at this. This is not good. So we lost the event that I was looking at. So what do I want to do now? Control right bracket quit. Let me get out of here. Okay, so this time, and I have a real event here, I'm going to have engineering look at this. So we panicked. I usually like to put a date on it too. Was it the 13th?
Yeah, looks like it.
So I like to give it some sort of meaningful timestamp. So UV con, E3, and I'm going to do the K dump. Oh, before I do that, sorry, Arch KDB. I was deliberately trying to get a large slab. Engineering's going to take a look at this whole call stack. Basically, I think the only thing I left running was LS. Okay, I'm going to do a BT here. The active running process looks like it was a sleep process. BT will give me the active one that was going on. Let me type in summary. And again, we had a lot of dirty data here, 75 gig. That was not good. Right back was under control again. And again, here, unreclaimable slab was the file pointers that we saw before we had the panic. So let me do a K dump. So I lost that workload characteristic. What I wanted to do was time and see how long it takes to trim and push down a large slab. Okay. How about we take a, where are we for time? Take a quick break here, come back at quarter after.
Okay.
And then we'll take a look at that USPS report, because with the system panicked, I don't have anything that I can do.
Okay.
Okay, so let's come back in 15 minutes.
All right.